numbers are going down. Yeah, that's beginning of the end. This is how it happens. Good morning. It is still morning, isn't it? Yeah, just about. Good after morning. Good after morning. Good after morning. Good after morning. Good morning, afternoon, after morning, whatever. Good after morning. Good after morning. After morning. Good 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 after morning.
Well, it is 12, isn't it? After?
It's it's in between.
Yeah.
It's a weird time. To see what it says. Let's see what the comments say. Good after morning. Good after morning, you out there. Brian, Estelle. Sticks for arms. Yes, I think that's a good idea. Is that Alex? Oh, don't know. Well, nice to see you out there. But, folks, if you post in, text in, message in, keep it clean, all right? Be good. It could be worse. It could be worse. I remember long time ago, I went to a restaurant with my dog. a little fox terrier.
Oh, that's cheeky.
And 10 minutes later, I saw a dog walking into the kitchen, and I thought, oh, look, it's a fox terrier. It looks exactly like my...
Wait, that's hang on.
That's mine!
Did you have to run after it?
Yes. Get it out of the kitchen.
Did it manage to swipe the goods before you got it though?
Well, unfortunately the manager wanted to speak to me. But it was all sorted all right. Indeed. I can't read that stuff. It's so small. Does it say? Math Science. Hi there. Hi, Math Science. Hi, Daniel. Nice to see you. Good. Oh, we are close to getting started. Hello, Rita. Well, my captain. Wow. I think people will refer to me as Picard. Yes, it is a two-sample t-test. That's what we are going to do. Does that help, Daniel? Okay, ladies and jelly beans, let's get started with probably the most important concept in statistics that you will come across as a scientist. Business as usual, don't forget to log your attendance wherever in the world you are. And if you are a professional, like our friend here, Daniel, you can go to Moodle as well and record your attendance, so that's absolutely fine. I don't mind if you have access to it. So the more the merrier. Anyway, last week I discussed with you the case of one sample t-test where we had basically a sample with some data, and we compared this sample to a single reference value. And I just abbreviate that as RV. That's the reference value. And we basically said we wanted to know what is the probability that we get this reference value when we have this sample. And I showed you how we can calculate a t-value in this case, and that was in particular, it was something along the line of the t-test value equals the sample mean minus the reference value, and we don't care about the sign of the whole thing, so we take everything plus, and we divide it by the standard deviation over square root n, or just simply by the standard error of the mean. And that gives our test t-value, and we can compare this test t-value just simply with a critical t-value and say, well, yes, it is likely that we get this, or no, it's not likely that we get this. And that was pretty straightforward. But unfortunately, life isn't always that easy. Sometimes life, as my PhD student once said, life is a bitch, and then you marry one. Sometimes you have two samples, and you want to compare. Are these two samples actually the same? Or is there a difference between these two samples? Here's a nice example that I picked up. So let's assume we just simply take and we measure the blood sugar levels of two groups of people. One group is the really sporty ones. These are the ones who, eat carrots. You'll never see me eating a carrot because I don't eat the food that my food eats. And the other one, these are the couch potatoes. These are the Krispy Kreme fans. And, So here are the data. One group, sample one, blood sugar levels, let's say 90 minutes after the last meal, whatever this meal was. Sample two, also 90 minutes after they had consumed whatever they prefer to eat. What would you say? Is there a difference between these two samples? If you look at the data. Is there a difference between these two samples? Is there a difference between the couch potatoes and the sporties? Emily, you are always good at making this judgment. What do you think? Is there a difference just by looking at the data? Yes, there's a difference. Yeah? Okay, who is going to go with Emily's judgment? Hands up. Who thinks there is a difference? Right. Who thinks there's no difference? I think we all agree there is a difference, right? From the data. By the way, any ideas where the blood sugar level in a healthy individual should be, say, 90 minutes after a meal? What is the range for a healthy individual blood sugar level in millimolar? Any idea? It should be between, say, healthy between 4.5 and, say, 6.5 millimolar under these conditions. That is where your blood sugar level should be. If you have elevated blood sugar levels under these conditions, that means potentially diabetes. Exactly. So sample one looks like they're pretty all right. Sample two, what do you think about that? See your GP. PDQ. Pretty damn quickly, right? Because you have a good chance of developing pre-diabetes, and then it goes downhill. So now, how can we compare these two samples? Because at the moment, we just asked you guys here what you think. Are they different? Are they really different? So how can we do that? Of course, we can say, surely they have different sample means. And when you do the calculations, and I need my pre-calculated stuff. So here the sample mean would be 4.55, and here the sample mean would be 13.67. So from the sample mean, we can see there is a huge difference between the two samples. And that would confirm what we thought. But wait a moment. We said whenever we take a sample, we get a sample mean, that's fine. And if we then take a sample, again, from the same population, it's unlikely that we get the same sample mean. It's just simply sampling error. Yeah? So actually we would expect to get two different sample means here. Now that makes it a little bit more difficult, doesn't it? How can we compare things with each other if we already know that they are different? I mean, the question is, how different is different? How much do they have to differ by before we say, oh yes, they are two different things? And in a way, there is no easy answer to that if we do it that way around. If we say we just simply compare the samples with each other, we run immediately into problems. Therefore, what we can do is we can use a different strategy. We can say, instead of comparing the different samples with each other, what we can do is we can compare, instead of the sample means, we compare the means of the underlying populations. We know that this sample here comes from, let's say, a population. Let's call that population 1. And we know that this population 1 has a population mean mu1. Now we can pretend that, let's say, this sample 2 that we have here, it could either come from the same population, population 1, or it could come from a different population. And we need to make a decision. Does it come from the same population, or does it come from a different population? So this would be our population 2 with the population mean mu2. And our question now is, instead of comparing the samples, can we actually compare the populations with each other from which the samples are drawn? And what we can say actually is, if the two samples come from the same population, then we would say, right, these two populations, and mathematically I can express that as the population mean of one sample is equal to the population mean of the second sample. This is if both samples come from the same population. And this is actually what is called the null hypothesis here. And the null hypothesis is abbreviated as H0. This is our sort of opening gambit. Both samples come from the same population, And the difference that we see from these two samples is just simply down to sampling error. So difference in sample means only due to sampling error. Nothing else. Now, the alternative is, we can say, actually, the two samples come from two different populations, and two different populations means the two population means are different. So we can write mu1 is not equal to mu2. So here, in words, it means the two samples come from different populations. Or in other words, the difference that we observe is, of course, down to, in the sample mean, is, of course, down to sampling error, because we always have sampling error, and an additional effect. So, for example, in this case, one group is lazy and eating unhealthy stuff like carrots, whereas the other group, is good. And this is called our alternative hypothesis, or usually abbreviated H1. And we haven't specified whether we think that one population mean is larger than the other. We just simply say they are different. These are our hypotheses that we have. And how can we test these hypotheses? Well, again, what we can do is we can do a t-test. But this time we have two samples. But the concept is exactly the same. We can try to calculate a t-test value, like we've done before, and we can compare this t-test value with a critical t-value, and then say, is this t-test value larger than the critical t-value? If it is the case, then we are sort of outside the range where we would things to be, where we would expect things to be, and then that's something different. So the t-test value in this case, most of you have done that in maths or something like that. But there is a slight twist to it. Because what you have been taught, how many people have been taught how to do a t-test? Hands up. Oh, not many. Oh, okay, excellent. Just simply to check with you whether I haven't lost you. How many people have not been shown how to do a t-test? Hands up. Right, so the total number of people who had their hands up is about 5. What happened to the rest? You have been shown, but you can't remember. Is that? Yeah, pretty much. Okay, now conventionally, you will be shown the traditional t-test. How you calculate the traditional t-value. And actually, The calculation is not terribly difficult, as I'll show you in a minute. The traditional t-test, or the calculation for in the traditional way, only works only when the numbers in the samples are fairly large and when the standard deviations, or rather the variances, for both samples are the same or pretty close. And I've written it just simply like that. Variance 1 equals variance 2. How are you defining population? Population in this case is basically everybody who we potentially could measure for their blood sugar levels. So I could measure everybody in that room here, or everybody in the UK population, or something like that. And with the population, it does mean that I have basically, when I do the population, I have all the information, there's no uncertainty. Does that answer the question? I hope so. Okay. So this is the traditional t-test that some of you have been taught. Now, if we look at our samples here, and if you care to, well, in one case we have 4 people where we measure the glucose level, so the sample is not really big. The other one is even worse. It has only 3 people in it, which is basically the minimum, the absolute minimum that you get away when you're doing a sample. Anything below 3 in a sample is just simply total utter nonsense. Doesn't make any sense. Now, if you calculate the standard deviation for both, you find that in one case the standard deviation is 0.7, whereas in the other case the standard deviation is, and it all goes downhill from there, 7. So they differ by a factor of 10. Therefore, our traditional t-test just simply does not work. It will actually give you total nonsense in this case. And therefore, what we could do is we can use a modified t-test. And you will find this in the literature described as what is called a t-test, or Welch's t-test, or Welch's test. And this Welch's test says we do a slight modification here, and we can use it if the numbers are small and if the variances are not the same. So that's this test. Now, what would happen if you did this Welch test, even if the numbers are large and the variances are the same, like in this scenario here? If we had this, And the numbers of the samples also need to be very similar in both cases.
Would it not matter on working like?
It would not matter at all. You're absolutely right, Katie. It would not matter if we use the t-test, the traditional, or the Wilks test in this case here. We would get roughly the same result. If we have small numbers, the numbers are not the same, and or the variances are different, we can't use the traditional, we have to use the Wilks test. So my advice would be always use the Wilks test, because then you don't have to think about it, which test you need to use in this case. Now, how do you calculate then the t-test value? Actually, it's not that bad. T-test, and we are talking about here the Wilks test, is just simply defined as sample mean 1 minus sample mean 2. And we want everything positive, so we just simply take the positive of what we get, and I indicate that by these two vertical bars. That's the absolute of it, divided by the square root of S1, the variance of sample 1 divided by N1, plus the variance of sample 2 divided by N2. If you like, you can write this in a slightly different form. Because what is this here? What is S squared, sample 1, the S squared divided by N1? There's nothing else but the standard error of the mean for sample 1 squared remember, for the standard error we said it is S over square root n, and if I square that, it gives me same squared. It would give me S squared, and the square root disappears, n. So that's exactly this one here. So we have x bar 1 minus x bar 2 divided by square root of standard error m1 squared plus standard error m2 squared. That's our critical test value. In the traditional t-test, what you do, just for those 3 people who put their hands up, you actually mess around with the standard error of the mean. So for those of you who haven't done the traditional one, just for 20 seconds, don't pay any attention to me what I'm saying. Just switch off, okay? In the traditional test, you mess around with the standard error of the mean, and you do an adjustment, you do a weighting, depending on the sample sizes. In the Wilks test, you don't do this adjustment. Now the 20 seconds are over, so please pay attention again. In the work test, you don't do this adjustment at that point. Where you do the adjustment is in the T critical. There you do an adjustment. And what you do is you adjust the degrees of freedom. The equation for that is a beast. How you adjust that? And you don't have to do it, right? There's no need for you to learn this equation. I can't even remember the equation. I can't even remember the name of the equation. If you want to look it up, I think it's Satterthwaite correction or something like that, where things come up with to the power of 4 divided by God knows what. But you don't have to deal with that. Because, I'll show you in a minute, the trick how you can easily do this calculation in my favorite program that can, according to Ben, even solve the problem in number 10 Downing Street and the nuclear situation in North Korea. As you can guess, it's Excel. I show you how to do that in Excel. So, we do this t-test, we compare our critical value with our t-test value. So let's say, for example, here is our t-crit. Here we know that we have 95%. And let's say if we do the calculation, we might find that our t-test value is, for example, here. That's our t-test. And we can now ask the question, what is the probability to get this t-test value out there? And that would be our p-value. Right? So, how do we get this t-value, p-value? How will we get this probability? The good thing is, in Excel, it has a built-in function The command in Excel is t.test. And then it asks for 4 things. It asks for the number. It asks for the numbers from sample 2. And in Excel, I think it is called array 1, array 2. Which way around, it doesn't matter. It then asks you whether you want it 2-tailed or 1-tailed. I'll come back to that in a minute. We always go for 2-tailed. So that's the 2. And the last one, it asks you what kind of test do you want. And for the Welch test, it doesn't tell you that's a Welch test, but the number for the Welch test is actually number 3. That indicates a Welch test. If you put in number 2, it will do the classic t-test, the traditional. But I told you, don't do that. There's no gain in doing the classic t-test. always go with the work test. Right, let's see what we get when we do that. Now, I've put in the numbers here in Excel. Let's see what is the p-value. So it is equals t dot test. You see it comes up with the right thing. It asks for the first array. Let's do that, if it lets me do that. Okay, that's the first array. Let's do the second array, sample 2. The moment. We want this. We said we want 2 tails, and I would always say 2, and we want type 3, that's the work test. And we get a p-value. P equals, that is our p-value. Our p-value. It's 15% p-value. Now, what on earth does that mean? 15%. It actually means that we have a 15% chance or probability that our 2 population means are the same. That is what this probability means. We have a 15% chance that these 2 populations are the same. Now, of course, what we need to do before we do anything, we need to set a sort of a cutoff for us. When do we think that the 2 populations are no longer the same? And very often, you set this as, let's say, 5%. If your p-value is below 5%, if p-value is smaller than, let's say, 5%, then you say, I believe populations are not the same. Or, in other words, you say, mu1, mu2, they are not the same. By the way, this 5%, we have seen that. That is our significance level alpha. And you can set that to whatever you want, but very often it is 5%. So, if the p-value is lower than our cutoff point, we say we don't believe that the 2 populations are the same. Or in other words, the 2 samples are actually drawn from 2 different populations. Or in other words, there is a difference between the 2 samples, as indicated by the difference in the 2 populations. If our p-value is larger than 5%, we can say still could be two different populations, but we can't distinguish between them. It could be that they are from the same population. It could be that they are from, well, actually, it's probably quite likely that they are from the same population. It means that we say mu1 equals mu2. Yes. It could be that they are from, that the two samples are from the same population. So, if our calculated p-value is lower than 5%, we say there is a difference between the two samples. And we accept the null hypothesis. That's this one here. Oh, sorry. If p is smaller, then we say that there is a difference between the two samples, and we reject the null hypothesis. We say, no, they are not from the same population. The populations are different. There is a difference between the two samples, which is not caused just by sampling error. If p is larger than the significance level, our cutoff point, we say, well, we can't exclude that they are from two different populations, but it's very unlikely. And as I told you, the mnemonic for that is if p is lower than alpha, if p is low, h naught must go. We reject it. We know that they are from different populations. If p is high, that's the red one here, if p is high, h naught can't stay. You have to say that with an Australian accent. You can't say that they are from two different populations. You fail to reject the null hypothesis. Now, we got a p-value of 15%. Are our two samples of the couch potatoes and the carrot eaters, do they have, is there a difference between their glucose levels, blood glucose levels? Well, 15% is higher than 5%, surely. That means we have this case here. Therefore, it could be that these two samples come from the same population. Or in other words, there is no difference between the two populations. There is no difference between the two samples. Which means we cannot, at this point, tell whether the couch potatoes and the carrot eaters have a significantly different glucose level. Or in other words, from this data here that we have, we cannot say that there is a difference between them. So Emily, I'm terribly sorry, but you didn't get it right this time. Thank God for that, because that would be overkill if you get it right all the time. So with a t-test, we can ask actually, are these two samples from the same population or from different population? And if our P is high, then we can say they come from the same population, there is no difference between the two samples. If our p-value is low, then we can say, oh, wait a moment, we have a very good reason to assume that the two samples come from different populations in this case. Now, of course, we want to know sometimes, is this, if the two samples come from from two different populations. So if as sample 1 and sample 2 are different, how different are they? And the way we can deal with that is, again, we calculate the effect size. Or Cohen's d. And the calculation for that, again, is pretty simple. We take the difference between the means and divide it by the average of the standard deviations. And that is sort of just a ballpark figure, but if this value is larger than 0.8, by convention, we can say massive effect. If it is lower than 0.8, but around between 0.5 and 0.8, there is a decent effect there. Anything lower than let's say 0.3 is, yes, there is a difference, but do we really care about it? Does it make a difference whether in a 50-gram crisp packet there is 50.2 grams of crisps or 49.6 grams of crisps? You wouldn't notice. That's what the Cohen's d effect size tells you. Does that make sense to you? So with the Cohen's d effect, we can tell whether there is a difference. Now, if we quickly go back to our data that we have here, what we can do and what we have done in the past is we can calculate a confidence interval. Remember, you've done that in tests, you've done that in the practical, in your first practical. You are going to do that in the BI 301 practical if you're doing that next week. You calculate the confidence interval with an upper and lower bound. And in this case here, let's see that I get this right. This would be the confidence, the 95% confidence interval for sample 2. It actually goes from -3 millimolar glucose to +31 millimolar glucose. That is our confidence interval. For sample 1, our confidence interval is much, much smaller. And I try to get it in the right position. Here is our sample 2 confidence interval. Sample 1 confidence interval. And it goes from, let me see, I've written that down somewhere. it goes from 3 plus 3 millimolar to plus 6 millimolar glucose. And if you are so inclined, you can easily check that with the data that I've given you. Calculate the 2 different confidence intervals just for fun and see if you get similar values. But what you see is that one confidence interval is included in the large one, in the big one. If you observe something like that, it clearly indicates to you that the 2 samples are not statistically significant different if one is included in the other. Likewise, if you have a scenario like that, that's the confidence interval for sample 1, and you get something like that for sample 2. You see the confidence intervals have nothing to do with each other. This means the 2 samples are very, very different from each other. Just by looking at the confidence intervals, you can see that. The samples are very different. So in this case, you would come to the conclusion the 2 samples come from, have nothing in common. They are statistically totally different from each other. And if you've got a case like that, hey, great. You don't even have to do a p-value or something like that. Also, sometimes you want to do it because you want to show that you have done the calculation. And if you want to publish your results, you want to show that you can do that. It gets interesting when you have a case like that. When the 2 confidence intervals overlap partially. In this case, you can't make a prediction. Are the 2 samples different from each other, or are they not? And because you can't do that, that is when you really have to get the t-test in, when you need to calculate p-value and see whether you should accept H0 or whether you should accept the alternative hypothesis. Does that make sense so far? We've come to an end for that. Next week, I'm not going to see you in the BI 308 lecture because you have enhancement week, but I see most of you then in the practicals. Go in peace.